Hi, I'm Bent Rolf Pettersen. Albert Einstein showed us the relationship between mass and energy. J. Robert Oppenheimer demonstrated this with the nuclear bomb. What is the physics in nuclear fission, and why do atoms release energy? I made a short video about this.
J. Robert Oppenheimer was the director of the Manhattan Project and the constructor of the first nuclear fission bomb. J. Robert Oppenheimer, 1904 to 1967, was a brilliant physicist. He is most known for his contributions to theoretical physics and for his role in developing the first nuclear bomb. He was the director of the Manhattan Project in 1943, where he led nuclear fission experiments and developed the nuclear bomb together with other famous scientists. The first nuclear bomb, Trinity, was tested on July 16, 1945. In August 1945, nuclear bombs were used on Japan in the bombing of Hiroshima and Nagasaki. Later, several other countries developed nuclear fission bombs, but the bombs have never been used in conflicts after the bombings of Hiroshima and Nagasaki. E equals mc squared is Albert Einstein's most famous formula, the mass energy equivalence formula. This formula tells us the relationship between mass and energy. Matter consists of energy bound up in organized physical structures through quarks. A quark is concentrated energy. Different type of quarks store/handles different types of energy. Through an operating system, an atom manages these quarks and energies. The atom puts quarks together in atomic elements, protons and neutrons. The atom uses the strong nuclear force to hold quarks and atomic elements together in a structure. With nuclear fission, atoms release some of the energy in their quarks. Nuclear power and a nuclear bomb are examples of this. Oppenheimer helped us understand the great energies stored in matter, first shown by Albert Einstein in his formula E equals mc squared. But how can matter release energy? In quantum entanglement, we have seen how atoms can communicate with each other over great distances. We therefore can assume all atoms communicates with atoms in the vicinity. Atoms are therefore aware of their surroundings. Atoms perform several tasks. The attractive force pulls atoms towards each other and creates atomic bonds and gravity. To preserve their structure, atoms also create a repulsive force. This force helps atoms' cores to keep distance, thus prevent the nuclei from colliding with each other. Collisions between the atoms' nuclei can destroy the atoms. More information of this will come later. The strong force holds the quarks and atomic elements, protons/neutrons, together in a structure. Other energies. Communication energies help atoms communicate with each other. We must assume atoms also perform other tasks. Dielectricity seemed to be the preferred method of sharing energy between atoms. Atoms also seem to have an operating system and seem to be able to act upon information received. Atoms seem to be able to convert energies trough atomic phase displacement. In atomic phase displacement, atoms convert energies to the energies the atoms need and prefer. If atoms are in danger of colliding, the atoms increase their repulsive force. If not, the atom's nuclei might collide and be destroyed. The increased repulsive force helps atoms keep distance even if they are moving towards each other. An increased repulsive force is released. This increased impulsive force is then absorbed by the atoms in the area. They will then in time have abundance of this energy, much more than they need. They then convert this energy to other energies, like dielectricity. This might be perceived as heat. We see this in friction, explosion, and other collisions. If the atoms can't get rid of the excess energy through these channels, atoms might produce and release energetic quarks, which might be perceived as light. If the repulsive force is not strong enough to prevent a collision between the atom's nuclei, we will have a nuclei collision. The force of this collision and the energy level in the atoms determines what happened next. If we have a soft collision, an atomic element like a neutron might be knocked out from the nucleus. If the atom has enough energy, it will make new quarks, put them together as a new atomic element, neutron, and replace the neutron. The atom then maintains its structure. The atom will be an atom with the same number of atomic elements, but with reduced energy for a while. The neutron knocked out from the atom is now a free neutron. A free neutron will be able to maintain its structure for a short while. But without an atomic operating system and the strong nuclear force, it will soon not be able to hold the quarks together. The neutron will then have to release all quarks. The free quarks will then either be absorbed by other atoms or dissolve. When a quark dissolves, it releases all the energy stored in the quark. We then will have an immense release of energy. In a nuclear explosion, a fission bomb, we have strong collisions between large, dense, and energetic atoms. The free atomic elements, like free neutrons, might in turn knock loose other atomic elements from other atoms. We then have a chain reaction which results in many free atomic elements and an immense release of energy. This is a fission bomb. In a fission bomb, an ordinary explosion results in strong and massive collisions between heavy, energetic atoms. When the same nuclear atoms are led towards each other more slowly, we also have a high release of energy. This is a strong release of the repulsive force, a strong friction, which release strong heat. This heat can be used to produce steam, which then can be converted to electricity through a generator. This is the fission process in nuclear plants. Radioactive matter is very heavy and energetic atoms. These atoms have a different quark compassion compared to non-radioactive atoms. Radioactive energy is in all atoms. But the matter we call radioactive elements have extra quarks which store this energy. When these quarks dissolve, we will have a strong release of this dimensional, radioactive energy. Normal atoms have problem with handling this energy. They have problem with storing and converting it. This increased dimensional energy can therefore disturb the communication and operating system of normal atoms. This might make them behave in a different way. When cells reproduce in an unnatural way, cancer, this is because the disturbance of the atom's operating system due to radioactive energy. Atoms use a lot of energy to perform their tasks. In order to be in energy balance, they must constantly receive the same amount of energy. 70% of the universe is dark energy. Dark energy is free energy units which are not stored and organized in energetic structures. Atoms constantly receive energy from dark energy and they are therefore able to maintain energy balance when performing their tasks. Atoms with reduced level of energy after replacing atomic elements due to nuclei collisions will through dark energy slowly increase their energy level. In time they will recover their natural energy level. This is an explanation of how atoms may release energy in nuclear fission. E equals mc squared explain the energy in matter. Nuclear fission shows us some of this energy. Bent Rolf Pedersen, 2023.